A classical bit is simple, 0 or 1. A qubit is also measured as 0 or 1, but before measurement it carries a richer object, a quantum state. The compact formula is psi equals alpha times 0 plus beta times 1. Alpha and beta are complex amplitudes. Their squared sizes become probabilities, so alpha squared plus beta squared equals 1. That rule means the state has to live on a kind of unit surface. After ignoring one overall phase that cannot be directly measured, every pure single qubit fits on the Bloch sphere. At the North Pole the qubit is definitely 0. At the South Pole it is definitely 1. A point halfway around the equator is balanced, measure it many times, and 0 and 1 appear about 50-50. But the equator is not all the same state. Moving around it changes the relative phase between 0 and 1. Phase is invisible in a single yes or no measurement, but it becomes visible when quantum gates make paths interfere. Measurement turns the arrow into a random classical result. The closer the arrow points toward north, the more likely 0 becomes. The closer it points toward south, the more likely 1 becomes. Quantum gates are controlled rotations of this arrow. An X gate flips north to south, like a quantum knot. A Hadamard gate can move a definite 0 onto the equator, creating a balanced superposition. So a qubit is not just both 0 and 1 in a vague way. It is a precisely steerable arrow whose length is fixed, whose direction encodes amplitudes, and whose twist stores phase. Quantum computing becomes powerful when many such arrows are combined, entangled, and rotated so wrong answers cancel while useful answers reinforce. For one qubit, remember the picture: probabilities from height, phase around the equator, and gates as rotations on the sphere. That is the arrow inside a quantum bit.